In this lecture, we will see the first of two types of techniques that are used for concurrency control. In other words, to make sure that transactions satisfy the asset properties in spite of concurrency. So these two approaches are pessimistic concurrency control and optimistic concurrency control. Okay. So a pessimistic approach or pessimistic approaches assume the worst, and they prevent transactions from accessing the same object. So they prevent two transactions from accessing the same object altogether. An example of pessimistic that we'll discuss in more detail is locking. Optimistic approaches, on the other hand, assume the best, and they allow transactions to proceed as if there are no conflicts that are occurring and as if they would not interfere with each other. But at a later point of time, the optimistic approach checks whether or not the asset is satisfied, and if it's not, then it might lead to aborts. Okay, so multi-version and timestamp approaches, which we'll discuss later on, fall under the optimistic approaches. First pessimistic approach that we'll discuss is known as exclusive locking. Okay, this is the simplest and the easiest. Each object is associated with a lock, and at most one transaction can be inside a lock. When a transaction T wants to access an object O, either for reading or writing, it needs to make sure that it calls the lock of O function. And the lock of O function will block if there is at least one transaction inside the lock. When that transaction leaves the lock by calling unlock O, then another transaction is allowed in. Okay, this ensures that at most one transaction has access to the object O at any point of time. However, once a transaction T has locked an object O, it can then read and write the object O multiple times. It doesn't need to call lock every time. So it can lock the object once at its beginning and then do all its accesses and then unlock it at its end. This should sound familiar to you because this is very similar to the mutual exclusion problem and solution that we discussed earlier. In fact, you could use any of those techniques here to implement exclusive locking. Okay, but that's kind of orthogonal to what we are discussing here because we are at the semantic level or the level of transactions over here. So once again, concurrency is important here because it means more transactions per second, and it means more revenues for whichever is the company running the server side. And exclusive locking has the problem that it reduces concurrency. Essentially, you're only limiting transactions to read so that at most one transaction can read any object. In real life, workloads have a lot of read-only or read-mostly transactions where most of the operations are reads. And even there, the exclusive locking approach is limiting these transactions to read the objects only one transaction at a time. But this is kind of not required because reads can be done concurrently. As you've already seen, read-read conflicts on the same object are really not conflicts at all because they return the same values no matter what order they're executed in. So the hint again, or the key here as we go forward to the next approach, is that it's okay to allow two transactions to concurrently read an object because read-read is not a conflicting pair. But when writes come in, you need to be more careful. Okay, so that's the next approach, which allows two different types of locks on an object. Or rather, the lock on an object can be held in two different modes, the read mode or the write mode. As long as a transaction is holding an object in a read mode, other transactions can also hold the lock on their object in the same read mode, which means that multiple transactions can be allowed to be in the read mode. However, when any transaction is in the write mode, no other transaction can be allowed in either the read mode or the write mode. This means that this is an exclusive lock. So the operation is executed out as follows. Before a transaction T reads an object O, suppose it wants to read an object O, it calls read lock on O. The transaction T is allowed in if all the other transactions that are inside the lock all are in the read mode currently. If any transaction is in a write mode, then T will have to wait. Now, what does the T do before it writes object O? So it calls write lock O. Once again, write lock succeeds, or the transaction T is allowed past it if and only if no other transaction is currently accessing the object O, meaning it has not locked object O. If T already holds a read lock on object O and it wants to now write object O, it can simply call write lock to promote its lock from the read mode to the write mode. Okay. Once again, this succeeds only if no other transactions are currently in the read mode or in the write mode. Okay. So both of these need to be true. Otherwise, the promotion will block and T will block. Okay. Well, finally, when unlock is called on the lock by a transaction T, it releases all locks no matter what modes they're in. So how do you guarantee serial equivalence with these locks? So that's the whole goal, right? We want to make sure that acid properties are satisfied, and so they are of course satisfied when the serial equivalence is satisfied. But how do you ensure that serial equivalence is in fact satisfied? So two-phase locking is a very popular technique that's used to guarantee serial equivalence. Essentially, two-phase locking says that a transaction cannot acquire or promote any more locks after it has started releasing locks. Essentially, it says that the transaction has two phases: the growing phase, where it only acquires or promotes locks, and then a shrinking phase where it starts releasing locks. And once it starts releasing locks, it cannot acquire or promote any more locks. Okay, so that's two-phase locking. You have a growing phase where you acquire or promote locks, and then once you're done with that, you have a shrinking phase where you release locks. When we're talking of phases, these are phases that would occur inside the transaction operations themselves. So each transaction has these phases while it's executing its operations. There's a variant of two-phase locking known as strict two-phase locking, where there is no shrinking phase. Instead, you release the locks only when you reach the commit point. Okay, so there is releasing of the locks occurs only at one point, at the commit point of the transaction. So why does two-phase locking, as we've discussed it, guarantee serial equivalence? Well, the proof is via contradiction, and here is the proof. Assume you have a two-phase locking system where serial equivalence is violated for two transactions T1 and T2. Because of the serial equivalence definition, it must be true that there is some object O1 where the conflicting operations in T1 and T2 are such that the tag on that conflicting pair is T1, T2. And there is some object O2, maybe the same object O1, maybe a different object, where the conflicting operation pair is the reverse, which is T2, T1. Now, because of the first T1, T2 pair, and because of the way the two-phase locking works, the shrinking phase, the growing phase first and then the shrinking phase, T1 must have released O1's lock in its shrinking phase, and then T2 acquired the lock after that, which means that T1's shrinking phase is either before or overlaps with T2's growing phase. Okay? That's just by definitions. But then using the same argument on B, we can argue that T2's shrinking phase is before or overlaps with T1's growing phase. Okay? However, this cannot be true because you can't have both of these statements be true, because the growing phase only occurs before the shrinking phase in each transaction. Okay? And that is the contradiction over here. So one of the downsides of locking is deadlocks, and so here's an example of a deadlock. So here are two transactions, T1 and T2. They are trying to do similar things but in slightly different order. So T1 is locking the object ABC123, and then it's writing to it, and then it tries to lock object ABC789. T2 on the other hand locks these objects in a different order. It locks ABC789 first, and then it tries to lock ABC123. And this is the interleaving of these two transactions. Essentially, at this point, transaction T1, when it's trying to lock ABC789, it ends up waiting for transaction T2 to release its lock on 789. While here T2 ends up waiting for the lock on ABC123, which is currently being held by T1. At this point, the transactions T1 and T2 are deadlocked. Each of them is waiting for the other. Okay, so this is shown by this wait for graph, where T1 is waiting for T2 to release the lock on object ABC789, and T2 is waiting for T1 to release the lock on object ABC123. Okay, this is an example of a deadlock where these transactions T1 and T2 will not make any more progress ever at all unless you do something about it. Okay, so deadlocks can happen in any system that uses a locking approach. So when do deadlocks occur? There are three necessary conditions for a deadlock to occur. When I say necessary, I mean that if there is a deadlock in the system, then these conditions are all definitely true. Okay, so these three conditions are as follows. Some objects are accessed in exclusive lock modes, which means that when a transaction accesses some objects, those objects are accessed so that no other transaction can access those objects. So these are exclusive lock modes. For instance, the write mode is an exclusive lock mode. Second condition is that a transaction holding a lock cannot be preempted. Okay, so a transaction doesn't necessarily just give up its locks just like that. And third, most importantly, there is a circular wait or cycle in the wait for graph that we have discussed. Okay, so we discussed a wait for graph for two transactions, but when you have thousands of transactions involved and transactions are waiting for each other to release locks, you can draw a wait for graph among these transactions. If there is a cycle in the wait for graph or a circle of directed edges, then you have a cycle and you have a deadlock in the system. So once again, these conditions are all necessary, which means that if there is a deadlock, then these conditions are definitely true. However, they're not sufficient. If these conditions are true, it doesn't guarantee that there is a deadlock. Okay? It doesn't mean there is definitely a deadlock. Okay? So the sufficiency is not true. The necessary is true. So how do you combat these deadlocks? Well, there's a few approaches. The first approach is lock timeout. When a transaction is not able to access a lock for a while, it times out and it aborts the transaction. This could be expensive, of course. It avoids deadlocks, of course, but it's expensive because transaction aborts might become very frequent, and timeouts might occur even when there is no deadlock, because the network might just be slow and transactions might be aborting just because they are facing timeouts because of a slow network. So a different approach is deadlock detection, where you allow deadlocks to happen, but you detect the deadlocks when they do happen. Essentially here you keep track of the wait for graph. For instance, you keep track of it via the global snapshot algorithm. You might recall the Chundy-Lamport algorithm, which we discussed at the very beginning of this course, and you could use that Chundy-Lamport algorithm, global snapshot algorithm, to capture the wait for graph and the detect cycles in it. Okay, for instance, you could do this periodically. If you do find a cycle, then you need to abort one or more transactions in that cycle to break that cycle and to ensure that there is no deadlock in the system. Okay. However, this still allows deadlocks to occur, so transactions might still end up waiting when they're in a deadlock before the next global snapshot algorithm is run and the cycle is broken. So a third approach that comes in is deadlock prevention, which completely prevents the deadlocks by violating one of the necessary conditions. Remember that we said necessary conditions, which means that these conditions are absolutely required for deadlocks to occur. So if you violate any one of the necessary conditions, just one of them is violated, that's sufficient for you to, that's enough for you to ensure that deadlock will not happen in the system. For instance, the first condition said that some objects are accessed in exclusive lock modes. This can be violated by ensuring, for instance, that all objects are accessed in read-only modes, meaning you don't have any exclusive locks. So in a database where objects cannot be written at all, where objects can only be read, you can never have deadlocks because the first condition is violated, the first necessary condition is violated, and it's never true. Let's go to the next condition. Next condition says that transactions holding locks cannot be preempted. Well, you can allow transactions to be preempted or transactions to, for instance, time out when they're waiting for locks. Again, this would prevent deadlocks from happening. The third condition says that there is a circular wait in the wait for graph. Okay, so this can be prevented by the following approach. There are many other approaches that can be used too to violate this condition, but here's one approach. A transaction locks all its objects in the beginning, so it knows all the objects that it's going to lock up front at its open transaction time, and it tries to lock all of them in the beginning. If all these locks succeed, then it proceeds, then the transaction proceeds. If at least one of these lock attempts fails, then the transaction aborts immediately. Okay. Because in this approach, a transaction never waits for another transaction to release locks, because either you access all your locks or you don't. You never have any edges in your wait for graph, and so you don't have any cycles in your wait for graph, because if you don't have any edges, you don't have any cycles, and so this approach would end up preventing deadlocks as well. So we've discussed the pessimistic concurrency control approach, which uses locks, but it's still limiting, right? There are still times when some transactions are having to wait for other transactions if you still use locking. And so concurrency is still not as high as we would want it to be. And you can make it even higher by using optimistic concurrency control, which we'll discuss in the next lecture.